Good evening, everyone. Thank you for coming all this way. Thank you for Sylvain for introduction. Today I'll be talking about summarizing logs, software logs, with Approximate Nearest Neighbor Search and large language models. My name is Sami Mourched. I am a data scientist at Centreon. Centreon is a developer of Observability platform that encompasses three products. We have infra monitoring product, a DEM product, a digital experience monitoring. And lastly, we are working on a log management tool software that will be in public beta in January. And I'm part of this team that works on log summarization as a feature to this new product. So why log summarization? Let's imagine a use case where you are RSE. You're responsible for maintaining and the uptime of a service for your business. And it's quite critical, so you're woken up at 3 in the morning and there's an alert, something broke down. So you have to fix it and you find out what went wrong. Usually you could maybe do a restart, but this time no luck, no restart. So you have to look and sift through millions of logs that are generated by your log system, and you have to, I would say, today we would say grok, or understand these tools, this giant mass of logs in a short time and restore the service. So you could say, today we have we have language models, and we could send all this data to language models. But language models are too expensive to handle all this mass of data. Second problem, all language models today have a context window that is at most 1,000 tokens. So you need to batch all this information. So this increases the time and the cost and so on. Maybe you say lately, as the last result, I do a sample. But the problem with the sample is you have a non-negligible probability to lose some patterns, and you don't get all the fine-grained details that make a representative sample of your logs. So today, the solution I'm presenting uses MinHash for efficient log embeddings, and IVF-PQ for sublinear nearest neighbor search. And with this pipeline, we will build a representative sample log. The data flow I will be presenting is log stream, 1,000 logs per second, for instance. Then you have a key shinglings plus a universal hash, and then you have an index, cross-sectional index, that allows this nearest neighbor search. Then the k-means sampling that allows us to group similar logs together. And then we have built this sample, and this sample will be sent to our LLM summarizer, an agent that we, I would say, customized for the purpose. And we get, at the end of all this process, a structured output that could be parsed and understood and could be useful to us. Okay? Now, I would be using for this talk a sample that I took from an open source hub of logs, and this is an Apar Spark log. I would like to show this because not everyone knows what are logs. So usually, software logs write this kind of information. Usually have a timestamp. Here you can find info. That is the log level, and you have some kind of message that tells you what's happened. And this is this is quite usual. Sometimes you don't have a log level. Sometimes the timestamp is missing. So you have all kinds of stuff going against you. Now, this is I would like to illustrate the cost challenge. Suppose you have to analyze just 1 million logs. This represents 35 million tokens, and the costs to analyze this, just for the input, would amount to $71. This is we suppose that the cost is $2 for 1 million tokens. And the processing time would be around 30 minutes, multiple AI calls and so on. But with smart sampling, with your approach, you have built a sample, so you have only 400 logs, a total tokens of 7,000, and the cost is 3 cents. and a single API call could take you just 10 seconds. So you have you decrease exponentially your 90% of your cost. The first thing I thought in my pipeline, I called it shingling. What is shingling? You have software logs, so you need to transform it into something that algorithms understand. Usually today we construct what we call vector embeddings. What are vector embeddings? They are constant length vectors that represent a sentence from a text or so on. But the problem with that is that neural networks cost too much time to process this data. So what we do is we build shingles. So a shingle here, I give you an example. We take, for instance, here the window is 2. This is a 2 shingle. This is the original log line. And here we have built, we have given the 10 first shingles, 15, 5/0, /0, and so on. What is interesting in these shingles is that they capture the local context. Similar logs have overlapping shingles. The order is important. Error timeout and timeout error are different. Why? Because R here in this part and this part are different. So shingles that you get are different. It's robust to small changes, and it's really fast. I gave the example of neural embeddings. Today you can go to an API from OpenAI and so on, and you can build neural embeddings. But the problem is that's too slow. You're gonna pay for this service, and the messages, the vector constructed would be 700 or 1,000 long vectors. And this doesn't work for a fast processing use case. And now I will talk about MinHash similarity estimation via hashing. Okay, so we have the log messages, we build the shingles, and now we need to construct a signature. A signature is a unique vector that represents that log messages. But at the same time, this hashing and must preserve the similarity. So 2 similar logs must have almost similar vectors and signatures. And this is what we do with universal hash functions. So we take the shingles and we convert them to the use with this signature. And what's interesting with the signatures, with this hashing function, and this allows us, we have a small probability of collision with the condition that we select a value m that's big enough, a prime. Usually that's a prime number, big enough to avoid this collision of shingles. So to avoid that 2 shingles have the same value. And this has a very interesting advantage, is that we don't need a fixed vocabulary. We took the shingles, we hashed them with numbers, and we construct a unique number that represents this shingle, and we don't have to construct a unique vocabulary that represents oral language. This is very powerful, because when you observe logs, you can say, I know what's at the beginning of the pipeline, but at the end, you may receive some unknown messages, and you're stuck, you're invisible to all this new vocabulary if you select just the first vocabulary you see. Now, I will give you an example. For instance, I'll take the letter H. So what we do here is that we take letter H, we use its text byte representation, we compute a shingle number, and we use 10 hash functions to construct the signatures. So each value here is the result of hashing with a single hash function. And so with this technique, we have built a single representation that represents the letter H. And we can do a hello word. And we have the single representation of hello. I would like to give an example that's also interesting. Why this is interesting? Because some people could make and put emojis in your log messages. And this is bad because Unicode and UTF, you have 1 million characters. But you need to transform this into something that is usable by your algorithm. So by using the bytecode, instead of 1 million character, you're going down to 266 bytes. So you have transformed this problem in another space, the simpler space that is usable for you. Okay? And now, here what we've done, we have gone from log messages and we built signature with hashing, shingling, and so on. And we hope that all our work so far preserve the similarity between logs, the nearest similarity in meaning between the different log messages. And now, since we have built this algorithm, we must find an index that allows us to query this signature that we built and have a very fast response time. This is where IVF-PQ comes handy. What is IVF-PQ? We take all the signatures, we do k-means. K-means means that we are regrouping similar vectors together in this what we call this areas, and each area has a polygon, has a centroid. This center represents this polygon, and we mean inverse vector because this centroid from now on represents the whole area and all the vectors inside this polygon. So when we need to query this when we need to find new vectors, all we do is compare this new vector with the centroids, and then we look inside the polygons for the nearest value, and this way we have built a fast querying engine that's quite simple. The PQ is very important because we use what you call product quantization. What is product quantization? It means that we simplify the representation of the signatures further by doing splitting the vectors into subvectors and storing just what we call code words, a code book. Okay, so we have 100,000 log signature vectors. Similar logs are quickly searched, and the inverted file index reduces search from ON to square N. And the product quantization reduces the storage needs. Why? Because we need to store this product, the value of these vectors in, for instance, a database for later use. So we did all this work with the k-means and so on, and we built our represented vector. This is just a sample of the 31st values from our sample. Now we have built the sample, and now we have to build a system prompt. We built an agent that is a summarizer. It's quite simple. You say you are a log analysis assistant, given a set of log message from an application. Your task is to extract the 10 most important events and summarize them in a timeline format. I chose this timeline format because I want to keep the time so you can build a storyline, something that allows you to say this event happened, and you build a storyline that allows you to understand the root cause and so on. And at the end, you get this. This is the representation. You see some errors and so on. And you are better equipped to answer the question, what happened and so on. So to recap, we reduced by 90% the LLM cost. We reduced the processing in seconds. And the smart sampling give us, with the k-means, a fast and representative response. You get the code to try this at home with this, the QR code. And thank you.